All right. Well, thank you guys for sticking out to the good end.
It's really good.
So I'm going to take a step back and not talk about PV. I'm going to talk about sort of the resource that powers our PV. And this task is an older one. So it actually comes from the solar heating and cooling program. So some of the things I'll be talking about is, of course, relevant for both solar thermal, some for CSP and whatnot. But first, just going to start off by giving a bit of a task overview, and then I'm going to throw out some concrete examples of some of the work that we've been doing in this one here. So again, we're divided into 4 subtasks. The first one deals with sort of data generation. So that's about measurements, models that produce data, and sort of evaluating some of these data sets. Then we have 2, which is about enhancement of this data and analyzing these data, solar irradiance data. So that's about quality control and how we are going to be able to enhance these for better usage, sort of with different stakeholders and for different new technologies. We got subtask 3 in forecasting. I'm not going to talk so much about that. That's DMI's work in this project. And last, we have outreach, which is I'm the task leader or subtask leader for in this subtask. So there'll be some focus on that. But as I mentioned, this is a joint project together with DMI, who is responsible for forecasting and also doing some analysis of some of their measurements and promoting that data as part of this task. But first off, let's take a look at one of the kinds of solar irradiance data. We can typically have them come from 3 different sources. They can come from measurements, so expensive. We can have them come from satellite estimated models, so they have a good coverage or decently accurate and quite cheap. And then they can come from weather models, which are somewhat inaccurate, but often have global coverage and are free to use. But first of all, satellite irradiance data is typically what we would choose to do a feasibility study of a project, and essentially used in all. But one of the challenges is that we don't really know which one to choose. So here we have the 3 most well-known providers of satellite irradiance data. And if we take a look at their data sets, it's right. This one is the most trusted, accurate, and validated. This is the most reliable solar database. And this has the lowest uncertainty available in the market. So clearly, as a user, it's not very easy to sort of choose which of these data sets to use when we want to plan a project. And that's quite important. They have different costs and they have different accuracies and whatnot. So what we try to do as sort of this independent group is to go in and benchmark these data sets and, not exactly tell you which one to choose, but at least give you an idea about, what are the different benefits to the different data sets and which ones have higher and lower uncertainties in different environments. So for that, we go and we take ground measurements. So they're a lot more scarce. Here we just see the ground stations that we use for this project. There's 129 globally. So these are high quality stations like we have at Riese here, and we have one in Lyngby. And then we go ahead and sort of compare how these data sets match up, where we take the ground measurements and sort of to be the truth. So here's just an example for Europe where we benchmark GHI, so that's irradiance on the horizontal. The stations is different rows, and it's the different columns, and the rows are the different data sets. And just to highlight here, we have the Lyngby station here, and what we're looking is the bias. So we can see the Solar GIS data set has a 0.9% bias, so that's not too bad. But some of them might have a bias of 4.5%. So that would be kind of harsh if you were to model it, a PV plant for that. And if we look overall, then we're able to say, okay, so actually of the tested 8 data sets or 6, we have Solar GIS that performs the best. And some of those other, data providers you saw in the previous slides have chosen not to participate in this study. But we are redoing this study in a couple of years because they've seen that this actually has value. At least one more of these commercial data sets will be on the table. So there's a report out on this from our task 16 that kind of gives some guidance to what data sets to choose and what the different trade-offs are. So that's some of the guidances. As I said, this is based on measurements or by comparison to measurements. And this is a whole different story, right? The reason we don't always use these for feasibility studies of projects is that they're expensive and they come with inherently with a lot of errors. I mean, this here is a picture recently taken one of our stations that kind of clarifies that you don't always get good measurements. And here's just sort of a list of some of the things you see. And my main point is just here, right? I mean, there's always some kind of errors in these data sets and you get gaps and whatnot. So in subtask 2, what we're working on is quality control of these data sets, because when we use these sometimes high quality data sets to benchmark up against the satellite data sets, it's important we only use the highest of the highest accurate part of these data sets. So what we've developed sort of a large variety of quality control methods. Some are sort of just analytical. You can apply an equation that gives you an idea how good the measurements are. But we sort of also found it's important to go and look at your data because we can detect sort of more things with the naked eye than we can necessarily just. So this here is just from one station here where we plotted here at the bottom left. You have sort of the maximum measured DNI, so the diode irradiance, as a function of the elevation azimuth. And we don't really measure anything here below 10 degrees. So in this case, it's because we have a building and we have a line of trees. So of course, anything that's shaded like that isn't really representative of the greater region around it. So we got to discard those kind of data sets. Otherwise, unlevel sensors are some of the other things that we can find with some of these quality control methods. Now, moving on a little bit into the domain of solar radiation modeling, which we also do a lot of work on. So of course, right, typically what we measure is the global horizontal irradiance GHI, which is on a flat surface. But from the previous presentation, you probably got an idea that we don't really put PV laying down. So for that, we need to transpose the irradiance to get a prediction of the irradiance in sort of the plane of the collector or the panel. Now, the most sort of advanced model and or most accurate at the moment, or the standard, is the Perez model. But that has one noticeable drawback, is that it has these discontinuities. And that's just because it's a model that was developed in the 90s when computer power wasn't that effective. So there were some limitations. So one thing we've done this year, together with the original author, is to have gone and updated this model and made it continuous, which is something that's necessary when you have higher frequency applications, such as like 1 minute data. So the red line here is sort of the new predictions. So the overall long-term accuracy is about the same, but we're able to use this model for a lot of other purposes, such as like reverse transposition, when you take irradiance on a tilted surface and try and back calculate what it would have been on a horizontal surface, for example. Shading is another thing we're quite involved with. Here we see a 2-axis tracker. And just to denote, I'm not trying to sell these. I personally don't really like 2-axis trackers, but this for a previous CSP project where we went in and sort of developed some algorithm where you can calculate shading for all kinds of shapes. And here's just a little bit of an illustration of how shading happens throughout a 2-axis tracking collector field. So the green ones here is the unshaded part, and it's actually modeled after a company called Helix Solar Collector. It's a company based out of Harshal that makes these 2-axis tracking. So what we moved on now is a collaboration together with Sandia, where we look more at shading on single-axis trackers. So right now, I think Nicholas was mentioning how a lot of them, that basically limited the equations that we have at having a uniform slope to calculate this backtracking. So the equation that we've developed now and are publishing here later this year, that's next week, is equations that we can actually go and model it with a sort of a variable terrain slope, which is what we're seeing sort of more of the new systems having once all the good graded land has been used. Another aspect is data access. So one thing is creating these nice data sets that we have, but actually being able to access them has been sort of a main challenge. So there's a network called the BRSN. It's a global network of measurement stations, but they run these super archaic files that makes it difficult to use. And that has sort of been limiting its uptake. So part of the Python library called pvlib now features sort of 10 or 12 different functions for accessing different irradiance data sets, including some of these commercials data sets. So that you basically just write a few lines of code, then you're able to get high quality measured irradiance from these 4 different networks or from these 5 model data sets. And with our new release coming up here also next week of pvlib 10.3, that will also be accessed for commercials data sets. And you think maybe this is a little bit trivial, but having quick access to irradiance data really sort of enhances these different analyses that we make. And if we can quickly switch between different data sets, we're able to get more insight and actually do more research projects and sort of figure out better models in the end. One other initiative sort of in our outreach program is to give access to more of this data also. So we have a website called solarstations.org, where you can go in and interactively sort of look where is the nearest high quality solar radiation measurement station. So in Denmark, we have two. You can go and check out this map. There's a Risø station and there's one in Lyngby. Otherwise, that's sort of the high quality stations in Denmark. Of course, DMI operates 28 stations, but those are not really maintained. The calibrations are bad, to say the least, and they only measure one component. And for that, we can't really do a whole lot of quality control like we can at our stations here. Perhaps the main outcome of our task is the Solar Resource Handbook, for short. So it's a collection of some 300 pages, and I don't recommend you read all of it, but it's more meant as a reference manual where you can go and read about the things that you like. And it's kind of the authoritative text on the matter, where I recently, for the new edition coming up in May next year, have written the chapter on quality control. So this, if you have any sort of knowledge gaps within solar resource assessment, I can highly recommend this book here, and there's a link here, and you have the slides afterwards. Otherwise, a bit of an announcement for next year. We'll hold the European PV-PMC, which stands for PV Performance Modeling workshop in Copenhagen. It'll be at the EDA conference in downtown. And that's sort of a joint venue together with the DG guys here and also Lyngby. Sandia National Laboratories, which has the PV-PMC conference in the spring in Salt Lake City. European Energy, and of course supported by EDP through our task work. So I can highly recommend attending that if you have an interest in PV performance modeling. We'll also have a task 16 meeting actually here at Risø, together with one of the wind tasks coming up here in April. So generally the tasks are somewhat, the expert that participate in it, but generally when we hold a local event, we'll also invite some of you guys, if you have a special interest in solar resource assessment, to attend. So you're welcome to reach out and contact me. My email is here on this last slide. So thank you so much.